Is it working? So, thank you to the organizers for inviting me. I'm really honored to be here. I wish you a peaceful and free life for the future. So this is about Kummer's conjecture. I reached on last Sunday, and that was the first time I read the program. And in the program I was scheduled for Friday afternoon. I was leaving on Friday morning, so I was a little bit confused. But then I looked at the program, and the first talk was on Kummer's conjecture, so I said, okay, somebody else is giving my talk, so no problem. So lucky, I talked to the organizers, this is not the case, so I have to give my talk, finally. And it's kind of complementary, because, well, we'll see why. It's good that Kummer Marty gave the talk, because I learned this problem like in September, so I don't know much about it. I was in Japan visiting my friend Shigeru Kanemitsu. He gave me this paper about two Chinese persons that prove something. I started reading it, and then the reference was about Rammurti. I said, okay, that's a good subject to try to do something. So what I will do is, it's Kummer conjecture, it's a classical conjecture, and very, very nice, but I'm going to do something totally elementary, just counting. These persons forgot to count something. I'm going to count it, and then I get it a little bit better. So what is Kummer's conjecture? I will repeat. Kummer Marty said it much better than I did, but let me repeat it again. So I start with a prime, Q, and we consider the cyclotomic field of Q degrees of unity, let me call it K, and the maximal real subextension inside it then we will call HQ the class number and HQ plus the corresponding one. So we know that the first factor is the quotient, which is an integer, and has a very pretty representation by the class number formula, like products of L functions of odd characters mod Q and some powers of 2, Q, and pi, something like that. So the conjecture is saying that, in fact, the asymptotic of the first factor is given by this function here. Let's call it J. Or that this product tends to 1 as Q goes to infinity. Q is a prime. Okay, so this is something like 1850, and 100 years later, 1950, Ankin and Chopla proved the first evidence about it, which is as Kummer pointed out, if this being close to 1, so this is the quotient of the first factor and this function, this being close to 1 is the same as the logarithm is close to 0, would be little o of 1. So they prove little o of log Q, which is already something, and for example tells that, so you see this says that the asymptotic is like the GQ of the logarithm, which means that something like that,
In particular, it goes to infinity, so there are only finitely many cyclotomic of class number 1. So that's already something. More evidence. This quotient was bounded by computation for small primes. Okay, but this evidence didn't last too much, since we believe this is not true, the conjecture in general. But it took long, and then Granville proved that assuming the Elias-Halberstam conjecture and the hardly deducible conjecture of K tuples, then Kummer's conjecture is false. Let's say only 2 comments. He didn't say this. What he said is one of these three conjectures is false. So we believe this is the third one. Another comment, to prove this is not needed the full K-tuple conjecture, but only the 2-tuple conjecture. But I wanted to say like that because he can prove something stronger with this conjecture. Or first, let me say these 2 conjectures. Maybe all of you are familiar, but so this is, by the way, is a very elementary what I'm going to say. So I'm going to prove the whole thing. So maybe it's good for students to see everything. So Elias-Halberstam conjecture. So this quantity measures the error that we make when saying that the primes in arithmetic progression 1 mod q is uniformly distributed. So, and we are only, as we already know by Kummer's talk, we only are interested in these 2. So it's the same with -1 here. And then we take the difference. This is not the Elias-Halberstam in general. This is what Andrew with Granville assumed, and it's enough. Then, so all these definitions, then the error up to x to the 1 minus epsilon is less than x to any power of log x. So we win all these powers where the constant depends on a and epsilon. So this is much stronger than what is known, the Bombieri-Vinograd theorem, which is at level 1/2. Be true. The second one, so it needs again a definition.
certain set of k integers is admissible if for all prime q there exists an integer such that q does not divide this quantity. So this is just a technical condition to say that the sequence P AIP plus 1 from I1 to k can have all the terms primes. Otherwise, it would be trivial, all of them are divisible by q, if this condition does not apply. So in particular, what they say is not only that they can be all primes, but they are really the number of times primes as it corresponds. So the cardinal of primes up to x, such that all these things are prime, is bounded below by x over log x to the k minus 1. So the probability for being prime is 1 over log x. I have k plus 1 conditions, so I have k plus 1 logarithms. And the same for minus. By the way, so now we know that for 2 is true, and the previous results in these terms in the twin prime conjecture was trying to improve a little bit von Wieber-Vinogradov to prove the two-tuple conjecture, which was simply going up 1/2 and it would be enough. So this is a very strong assumption. In some sense, which I'm not saying, might be stronger than this one. They're not, they're independent things. So I was saying that this, assuming these two conjectures, the Kummer's conjecture is false. In fact, he proves something else. So if we call omega q the sets of quotients, and then we consider the set of limits, of these sequences, then this set is everything.
How do you say that k equals 2? You said it's true?
Well, it's like for p and 2p plus 1. In fact, I'm saying that it should be true after twin primes. No, not that. Okay, so it is false, but it's not very far to be true. So then also Granville proves that for every, this is the same paper, in the same paper he proves all these results. So for every C sufficiently large, the cardinality of primes such that the quotient is bounded has a density which is positive, and in fact this density tends to 1 as C goes to infinity. Then Ramurti Petridis, I think, they improved this in the sense that in fact exists. Well, by the way, this was I think, as a consequence of this paper, very soon later, they proved that in fact there is a constant such that the same is true for that constant, and not only for density, positive density, but for density 1. And also in Elliott-Harmstan, then we can replace 1 over c by 1 minus epsilon and c by 1 plus epsilon. Okay, so this is for almost all primes. What about all primes? So what can we say if we don't want to remove any prime? So this is what Kummer talking about in his talk. So there are two types. So remember, this is something about the product of L functions. By the way, the product of L functions is the quotient of two positive things, so it is positive. So it doesn't matter if I put this or the absolute value. And we want to know that this is like 1. This means that let's take the logarithm. Is something like that. So what does it mean? The logarithm of a quantity is small because this thing cannot goes to infinity, but cannot go to 0 either. None of them are here. I mean, we have to avoid these two parts. The part that when the L function goes to 0 means try to avoid single zeros. So the lower bounds of this quantity will depend, as Kummer showed us, in the single zeros of the L function. If we remove the single zeros from the picture, then these two problems are equivalent. So if we say, assuming there are no single zeros, or just take a conductor without single zeros or something like that, so then we can just stick ourselves to upper bounds, because it's going to be the same. So without single zeros, for example, means consider Q, which is 1 mod 4. Because if Q is 1 mod 4, then the Legendre symbol is 1, so it's even, so it's not there. So let's say here Kummer-Marti did the lower bounds and what is the relation with the zeros. And what we will do is just look at upper bounds. And then the results were Tatusawa in 1950. He can prove that this is like so taking logarithms, let's say, or let's put it like that. So he will prove that this is a power of log q, which means that the logarithm will be log q, bounded by log q, with an undetermined power. So he didn't care what was this power of log. Then 1980 something, I don't remember. So this, what he could prove is put a precise power to be 5. Then Lu and Zhang, which is the paper that I read, and what we will try to improve. By the way, this is a joint work with Kanitsu. So they put here 7/6, and finally it's a little improvement, or 1/6. By the way, this little improvement is exactly in the part that Kummer-Marty said is negligible. So we will have to look a little bit carefully at this part. Okay, so then let's start the proof. So let's consider the logarithm of so if we want this to be what I said there, then, so I want to put a 1 here, that means that this sum must be like log q, with a constant 1 in front. So we're looking at the constant that multiplies log q here. So the idea is just to split this sum. This is the same idea, so this is the same argument as in previous works. Split this sum properly and study each sum in a different way. So this sum will take 4 factors. And clearly this will be less than each of them. So we want to bound these 4 absolute values. S1 is small primes Oh, by the way, let me write. So what is this? So what happened here? This is a converted sum. So this should tend to 0 if B is big. But we need an explicit bound in terms of Q. And here, how many characters we have? We have Q minus 1/2, which is of order Q. So we really need this to tend to 0 faster than 1/Q. It's not only that tends to 0, but very fast. So we need to get B big. So what is, after, this is tricky, to get the B so everything matches is well, is a point to look at. So let's take B equal to Q log Q. Which is something like that. So it's bigger than any power of Q, but smaller than the exponential. So, okay. So S1, so what is S1? We are summing over odd characters, so we still have orthogonality relations, and the orthogonality relations would just recover primes which are 1 mod Q or minus 1 mod Q. So this is like Q minus 1 over 2, the sum of primes which are 1 mod Q, oops, minus of 1 over P. What I'm doing is just inverting the order of summation. Okay, so if we want to have an upper bound of the absolute value of S1, what we are going to do is just forget about this part. So this is clearly less than this part, and forget about this part. And that will be a bound for the absolute value. I'm not going to do both because are the same, so I will just say that this is less than this. Okay, very quickly. So this is by Brun-Tishmars. So this is partial summation. What I will have is the number of prime which are in a certain congruence class. This is bounded by 2 times pi of x over q minus 1. So this is 2 times over q minus 1. And now what I get is here p up to b, which is log. I'm sorry. So this is partial summation. Which is like this, bounded by this. Now I just use Brun-Tishmar here, so I get 2 over q minus 1, 1 over t log t. This is the log. So I have log b times 2 over q minus 1 times q minus 1 over 2, which I get a 1. So the constant 1 comes from this part. So this is exactly the part that gets some the important part in the estimation. Log b, by the way, is exactly log q plus log q, which is negligible. So this is S1. For S2, I will not do it. S2 is the big primes. So this can be proved. That is little o of 1. So it's negligible, and the proof is a little bit more, it needs more work, but it's simply the same formula. Now, without removing this part, I take the error in both, and then I need to use an explicit formula for the function. I remove the main term. If we assume, oh, by the way, this is assuming there's no Siegel zero, okay? In the whole work, I am assuming that there's no Siegel zero. So there's no Siegel zero, this will be the error term. The error term is the sum of certain zeros of the function, and it can be bounded. I'm sorry because I'm very bad in time now, so, but this is done. This is already done in the works of Sun and some others. So let me concentrate in the other two, which are I'm finishing in how much? 5 minutes? That's very bad. So what is, for example, S4? So let's look at a crude estimate. Or maybe let's do S3. The smallest, and I can explain you a little bit something. So again, I use orthogonality. I forget about the -1. It should be done, but it can be done in the same way. So I get this thing. Oops, I'm sorry. And I forgot an N here. I get this part, and then so what is this? If I want to keep this one as a constant, it's better that this is less than log q. But maybe it's even little of 1. So what is the problem here? Since p to the n is 1 mod q, that means that p to the n is big. No? It's comparable with q. No? Must be big. Q divides p to the n minus 1. So there's a q here, but there's a q here. So how am I going to do? I should prove that this is very small. But what happened? If I take the primes which are small, so there are two parts, primes which are small with n big, and primes which are big, and then n is whatever. Big to reach this condition. So let's take the primes which are small. So let me say this is easy because the prime is big, and then here I will have in fact I have a congruence class here. I have several congruence classes. So these congruence classes tell me that this is like multiples of q. Multiples of q here would be q to the n, and n is bigger than 2. So this is negligible. This is easy. What about this? What happened? Let's suppose, so p to the n is 1 mod q, in particular n is a multiple of the order of p in fq. So take, for example, a prime which is of order 2, a prime which is like the square root of q. So that would say a square root of q square is q. I have a 2 here, so it's impossible that this is negligible. There's something here, right? So I need to bound this something. It shouldn't be too much. So why is not too much? So maybe I will just forget about S4 and leave you as an exercise this one. So let's concentrate in this one, and then so as I said, this is the sum in primes less than q, and now the sum of n's which are multiples of the order of p, let's call it EP. So that would be p to the k EP, and here 1 over EP, and here a k, something like that. This is a geometric progression. I can forget about this k. So this is like taking the first term. So that would be So it turns out that studying this sum is the same as looking at the order of prime P in FQ. So let me do two different cases. Suppose EP is prime. So this is in two sums. So let's look at the composite one. So if EP is composite, say is A times V, so then Q divides P to the EP minus 1. But this is P to the A minus 1 times P to the AB minus A plus things, which are small. So in particular, this is the order, so Q does not divide this, because otherwise then, okay? So Q must divide this, so P to the AB minus A, Q is less than this. So we put it there. Oh, 3. So what we do is just write P to the AB, P to the EP is P to the AB minus A times P to the A. This is bigger than Q, so this is smaller than 1 over Q, that kills this part, and I have P to the A there. So I will have here the sum 1 over P to the A is bigger than 2, because this is composite, this is convergent, and that's okay. This is a constant, which is less than log. I mean, it's less than anything that depends on Q. So let's go for the other one. So we use the same idea. Now, so if EP is prime, this is 1. And, can I have 2 minutes? Thank you. So this is 1, this is whatever, the prime that corresponds. So here I would have P minus 1, B minus 1. So P to the B minus 1 is bigger than Q. So I do the same, but what I get now, the Q, I cancel it, and then what I get is the sum of 1 over P, it remains, this here, and I have to say now the sum of the primes, the possible orders of P, such that L should be, so this is L, so this is less than log D. Here I have 1 over L, and I have this. In particular, how many primes could be of order L? So these are solutions to x to the L congruent with 1 mod Q, so there are no more than L. And moreover, the biggest the prime, I mean the smallest the primes, the biggest this quantity. So the worst case is when the first L primes are the solution of this equation. So we just put the primes P less than L, log L, right? Like prime number theorems, whatever, I don't care about this part. And this is like log L. So this is less than log L divided by L, sum L. I forget about this part, L that's less than log B, L prime. And what is this? This is simply log square. And that ends. Thank you.